writing this term on the other side, minus 1 over theta times d by dt of e of u of t minus e of psi power theta. So that's what you're going to get. Okay? And what I would like to show next is that this integral for sufficiently bigger t to infinity, in other words, this integral from sufficiently bigger t to infinity is finite. And this would be finite if this side is finite. If this side is finite. Now, for sure this side is finite. Why? Because if you simplify this, you're going to get minus 1 over theta e of u of t minus e of psi power theta, okay, because this derivative, the integral will get this, and you're going to have 0 to infinity. So first you need to kind of substitute the limit infinity, but by substituting limit infinity, so I know from the step 1 that there is a sequence in Tn that goes to infinity for which u of Tn converges to psi. What follows from this is that e of u of Tn will converge to e of what we will call psi actually, as Tn goes to infinity. Now, in other words, if you're going to substitute this, this will also become e of psi. So the first term will be 0 plus 1 over theta. If you substitute the second limit, which is capital T, you're going to get e of u of capital T minus e of psi. This is what it is. But I can assume actually that T is sufficiently big for which this is true. So e of u of T is bigger than e of psi. Okay? So in other words, this difference is a positive number, and hence it is finite actually. So this difference is for sure finite by assumption. So if this is finite, this t to infinity u t dt is finite actually. And if this is finite, this means that norm of ut belongs to L1 of, so it's integrable from t to plus infinity. Okay? So this is true. And this is true, you know, for any sufficiently big d actually. Okay? So you can take any sufficiently big d and you have it. Or you can say that if it is true in general, then this is true actually. That ut, it is not difficult to see that this belongs to the L1 infinity of the entire interval 0 to plus infinity. Okay? On the entire interval 0 to plus infinity. And if this is true, then here is the key thing that we can have. So if this is true, then I can say that if I integrate from s to t, this ut say with respect to d tau, this is less than or equal to the integral of the norm of ut from 0 to infinity. And it is finite, so this must be finite actually. And on this, if I, for example, and you know, it is not difficult to see that this integral, okay, can be kind of can estimate really. So this integral can estimate really what we call the u of t minus u of s in L2 norm. So this is L2 norm. Okay, and this really shows that u of t converges. So this is true for any t. Converges as t goes to infinity in L2, what do we call omega. Okay? So this converges in really L2 omega. And if it converges in L2, Okay, in L2, in other words, say it converges, and we know that at one sequence that it converges to psi. Okay, so if it converges to some L2, then we know that this, these trajectories of what do you call the orbits? Okay, they are relatively compact. So they are relatively compact actually. Okay. So if u of t converges to some point psi, in L2, and such, for example, orbits are relatively compact, then you're going to say that u of psi of t, and we actually know that it on one sequence it converges to psi. So you can say that you're going to find a subsequence. You're going to find a subsequence. So let's call this subsequence again Tn. That you're going to find a subsequence of say sequence Tn. Let's again denote it by Tn. You will converge to what you call the same psi in H norm as what you call n goes to infinity, or as Tn goes to infinity. Okay, so the relatively compactness tell you that if you take a sequence, okay, then it always have a convergent subsequence actually. Okay, so if you treat u of t as kind of a sequence, or u of t and as kind of a sequence, it has a convergent subsequence in H actually. Okay, because H is relatively compact because of the relatively compactness of what you call these union of trajectories actually. Okay, and this is what that really you needed to show it. So I hope you got some vague sense. I've left some gaps actually. You can fill those gaps. So what does this result is essentially telling you that the solution of nonlinear reaction diffusion equation converges in long run in H norm in the H is the space from which you are taking the initial data. It converges to some equilibrium point psi, which is a stationary solution of the nonlinear evolution equation actually. Okay, this proof is good, but one thing that I'm leaving for you is to do is that there is a really beautiful proof, okay, an equivalent and even an easy proof actually. So I have done the difficult task by M.A. Jandubi, Muhammad Ali Jandubi. Okay, so he proposed, so it's also given, if you're going to read the notes after this proof, the next M.A. Jandubi proof comes actually. So try to make sense of it. Try to understand it actually. So it's a really compact and short proof than this long proof.